So this is lecture of chapter 16, second lecture in chapter 16, masses of atoms. We will understand the meaning of the atomic mass unit. Atomic mass unit. We will understand what the meaning of the atomic number and what the meaning of mass number. We will calculate together the average mass of some natural elements, and we will understand what the meaning of the half-life. So the atomic mass unit is a unit which is used to measure the masses or to calculate the masses of very small particles like the atoms or molecules and so on. Because we couldn't use the kilograms or the grams for these very small particles, or the error will be very high. Okay. So for example, if we look at the neutron, its mass in kilogram is around 1.674 times 10 to negative 27 kilogram. And to be very precise, you need to say it's 74929. And maybe you can add more decimal numbers. Okay. So the kilogram and the gram and these traditional units are not working. So we need something else. So what do you think if we want to assume a new, or we want to invent a new unit? Some people might say, let's take the unit as the mass of hydrogen. So let's take the mass of hydrogen, because it's the smallest atom, the mass of hydrogen, to be our standard. And let's say this is 1 unit. 1 unit. And we will measure all the masses, okay, in terms of the mass of hydrogen, because the mass of hydrogen is 1 unit. Actually, some of the scientists, they did that in the 19th century. They took the mass, or they considered the mass of hydrogen as a standard mass, and they measure all the other masses of the other elements in terms of the mass of hydrogen. But later also they found that it produces many errors, so they changed this idea and they considered something else. What did they do? They said, okay, let's take the oxygen atom. They knew at this time that oxygen has 16 particles. Okay, so oxygen has 16 particles. 8 of them are protons and 8 of them are neutrons. Okay, so we have here 16 particles. We call them nucleons. Nucleons. The nucleon is a proton or a neutron. The nucleon is a proton or a neutron. We call it nucleon. Okay, so the oxygen atom, or the nucleus of the oxygen, has 16 nucleon, 8 protons and 8 neutrons, which is good because protons and neutrons, they have slightly different mass. They are almost the same, but the neutron is a little bit bigger than the proton. Okay, so they take an atom with the same number of protons and the same number of neutrons. And also this kind of atoms, which is the oxygen, is spread everywhere. You can find it in most of the reactions. Okay, most of the compounds have oxygen. So they said, okay, we will measure the mass of this oxygen and we will divide it over 16. So this gives us what? What do you think? If we measure the mass of this atom and divide it over 16. So the result here expresses what? What do you think, guys? Can anybody tell what is the meaning of this result? This should be the average mass of a nucleon, average mass of proton or neutron inside the nucleus. Inside the nucleus. Okay. So they said, okay, we will take it as a reference. After 50 years or 60 years of using this method, the nucleons doesn't have U, by the way. It's NuC, nucleon. Okay. Nucleon. So after 50 years or 60 years, I think by the end of 1959 or 1960, they decided that the mass of oxygen, it makes some troubles in the calculations, especially for the physicists, because people who use the oxygen were mainly chemists. So for the physicists, it makes some of the problems in the calculations, especially that they discovered some isotopes, nadha'ir, okay, for the oxygen other than the 16. So they found that there are multiple isotopes for the oxygen, not only the 16. So they decided to decrease the error to change this atom and use a different atom. So they decide finally to use carbon. And they used carbon 12. What's carbon 12? It's an atom. Its nucleus has 12 nucleons, 6 protons, and 6 neutrons. So they said we will measure the mass of this carbon and divide this mass over 12. So this gives us what? It also gives us the average mass of a nucleon, proton or a neutron, inside the nucleus of carbon 12. And they called it the AMU, the atomic mass unit. And since then, the atomic mass unit, which is the mass of carbon 12 divided by 12, is one atomic mass unit, and everybody uses it as a reference for the measurement and calculations in the nuclear field and in the chemistry field. So one atomic mass unit actually is the mass of carbon 12 atom divided by 12. So if we try to change it, the one atomic mass unit into kilogram, this is the number. You don't need to memorize it. It's 1.66 whatever times 10 to negative 27 kilogram. You don't need to memorize the number. Okay? We will give it to you in tables if there is a question about it. If you look at the free neutron or the free proton, you will find that the free neutron or the free proton have more mass than one atomic mass unit. So they have higher masses than the average mass inside the nucleus of carbon 12, or generally in any atom. They have more mass than the mass inside these atoms. So why is that? Why the mass of the free neutron or the free electron, the free neutron or the free proton is higher than the mass of the same proton or the same neutron if it is inside the nucleus? Can you tell? Do you have any idea? You can guess.
Because of electronaut?
Not the electrons. Electrons, it makes no change, because if you look at the mass of the electron here, it's very, very small. It's 0.0005. The mass of the electron is almost like 1 over 2000 or 1 over 1800 the mass of the proton or the mass of the neutron. Very small, very small. So they usually neglect the mass of the electron in calculations. If we try to calculate the mass of the atom, usually we neglect the mass of electrons because it makes no difference. So this is not the cause or the reason. There is another reason. What is it? Part of the mass of the neutron and the proton changes into energy. Why? Because this energy is used in the binding energy inside the nucleus. Inside the nucleus, there are nucleons, protons and neutrons, protons and neutrons, proton, neutron, proton, neutron. So how can you collect all of these particles together in one place? There must be attraction force in between. Okay? It's some kind of potential energy in between. we call it the binding energy. The binding energy. Where this energy come from? If you look at this equation, you will know. Have you seen this equation before? The Einstein equation, E equals mc square. Huh? Have you seen this one before, guys? This is the relation between the energy and mass. Okay, so at the level of atoms or the level of subatomic particles, okay, this equation works very well. The mass can change into energy or the energy can change into mass. So part of the mass, this difference in mass, it changes into some kind of energy. Which kind of energy? The binding energy. What is the binding energy? It's some kind of strong nuclear forces. If you remember when we studied physics and we studied the forces, we said there are traditionally 4 kinds of forces in the universe. There is the gravity force, the electromagnetic force, and the strong nuclear force and the weak nuclear force. So the strong nuclear force is the force which is responsible to attract the quarks together. Do you remember the quarks that we have studied last time? We said neutron has 3 quarks and proton has 3 quarks. So these quarks are attracted together by the strong nuclear forces. And also the nucleons, which are the protons and the neutrons, they are attracted together using the strong nuclear forces. Okay? So that's why there is a difference between the mass of the free neutron or proton and the mass of the same particle inside the nucleus, because part of the mass is used as binding energy. Okay? What is the atomic number and what is the mass number? Atomic number is the number of protons inside the nucleus. Number of protons inside the nucleus. What is the mass number? Number of protons plus the number of neutrons inside the nucleus. So one of them is the protons only. That's the atomic number. And the other is the protons plus neutrons, which is the mass number. So the mass number equals what? Equals the atomic number plus the number of neutrons. Okay? The atomic number is unique. It's unique for every element. So the atomic number of hydrogen is 1. Atomic number of helium is 2. And so on. Atomic number of boron, 5. Carbon, 6. Nitrogen, 7. Oxygen, 8. And so on. So each element has its own atomic number or its own number of protons. Okay? But not the mass number. Sometimes the mass number is common between more than one isotope. And we will see what the meaning of isotope later. If we have some elements like these in the table, let's say we have boron, we call it boron 11. Boron 11 has 5 protons and 6 neutrons. So what is the atomic number of boron 11? What is the atomic number? 5, that's right. What is the mass number of boron 11? The mass number. 11. Mass number. 11. Its name is boron 11. So it's 11. Okay. Let's take sodium 23. Sodium 23 is an atom that has 11 protons and 12 neutrons. So what is the atomic number of sodium? Atomic number?
11.
11. And what's the mass number of sodium?
23.
23. So the mass number of sodium 23 is 23. It has 12 neutrons and has 11 protons. Okay? If you look in the periodic table, at the top, these numbers are the atomic numbers. These numbers are the atomic numbers. Okay? And we will study the periodic table in like maybe next time. Okay? So let's look at one of the examples. Let's take fluorine. Fluorine 19. Its symbol is F. So we write down the atomic number in the subscript and the mass number in the superscript. So the fluorine has 9 protons, so its atomic number is 9. And it has 19 nucleons, so its mass number is 19. So how many protons in the fluorine? 9. How many neutrons in fluorine, guys?
10.
10. That's right. Excellent. So if you look at the atomic number and mass number, you can get the number of protons and number of neutrons, and vice versa. If I give you the number of protons and neutrons, you can get the atomic number and the mass number for any isotope. What are the isotopes? What does it mean, isotopes? Do you know, guys? نظائر. What does it mean? What are they? Do you remember maybe from the high school?
Same in atomic number.
Again, what is it?
They have the same atomic number.
They have the same atomic number. So they are some versions of the same element. Some versions of the same elements. So they have the same atomic number or the same number of protons. They are the same. Okay. But different what, guys? Different number of what?
Of neutrons?
Neutrons, that's right. But different number of neutrons. So the isotopes are different versions of the same element. All of them, they have the same chemical properties, okay? But they have different number of neutrons. All the elements that you find around you, they have different isotopes. And usually, these isotopes are found naturally. Of course, some of the isotopes are made in the lab. Some of the isotopes, or most of the isotopes actually, are made in the lab. But of course, any element has a natural isotope that you can find it in nature on the Earth. For example, hydrogen, we thought that it has only one kind, but hydrogen actually has 3 versions, 3 isotopes. The first one that all of us know, which has 1 proton and 0 neutrons. This is the one that we have studied since the elementary school. So it's H11. It has a name in physics and chemistry. Sometimes we call it protium. If we are talking about isotopes, so we call it protium. Okay. There is another isotope which has also the same proton, but it has 1 neutron. So it has a proton and the neutron. It's 1, 2. We call it deuterium. Its name is deuterium. And there is a third one. It has also 1 proton, because all of them, they are the same in protons, but it has 2 neutrons. So it has 3 nucleons. So it's called H13. We call it tritium. So we have protium, deuterium, and tritium. These are the 3 isotopes of hydrogen. The first one is the most common one. So you will find it in any sample, 99.99%. So the percent of this hydrogen is 99.99% of all the hydrogens on the Earth. The other one is only 0.01%. The deuterium is only 0.01, very rare. Tritium, it's very hard to find it. Just a trace of tritium can be found somewhere. Like actually, most of the tritium is made in the lab. Most of the tritium that we have is made in the lab. But naturally, it's very, very rare. Okay? I cannot give it a percentage. I can say 0.00000 whatever. Okay? So it's like a trace of tritium. So the masses of these isotopes are, the mass of hydrogen is around 1 atomic mass unit, which is the mass number of hydrogen. This is the protium. The mass of the deuterium is 2 atomic mass unit. The mass of the tritium is like 3 atomic mass units. By the way, these are the mass numbers. The real mass is a little bit different from the mass number, by the way. So if we look back to the mass number, this mass number, it's very near, we can say, it's very near to the real mass of the atom. It's not exactly, but it's very near to the real mass. The hydrogen, for example, the real mass of the protium, is around 1.007825 atomic mass unit. But here I said it's 1. The mass of deuterium, the real mass of deuterium is 2.01410. Of course, there are tables. I don't memorize it, but there are tables for these numbers. Atomic mass unit. So this is the real mass of deuterium, while I took it as 2, which is a good approximation if we make a rough calculations. But if we want to make the exact calculations, we have to use real masses, not the mass numbers. So the mass numbers are fine in chemistry and also are fine in the rough calculations. So if I ask you, what is the mass of hydrogen? Which one you will say? Is it 1 or 2 or 3 or what should I do? Can you guess? Any idea?
1.
Somebody will say 1. Why 1? Why not 2? You will say because it's 99.9%. So that's a good guess. What if we have an element that has 2 isotopes, for example? Okay. And the first isotope is 50% and the other isotope is 50%. Okay. Which mass of them you will take? What do you think? So we need an idea. So they decided to use the average mass of all the isotopes, not any one of them. So they calculate the average mass of the isotopes. How to calculate the average mass? Should I say 1 plus 2 plus 3 divided by 3? This will give me the average? Of course not. It's not going to work because the protium is 99.99%, while the other one is 0.01, and the third one is almost 0. So they said, okay, we will multiply the mass times the percentage. Mass times percentage. Mass times percent. Of course, this percentage is almost 0. And then add all of them together. Add all of them together. And divide it over 100. So this will give you the average mass. So we have an equation to calculate the average mass of for certain element or for certain natural element using the masses of the isotopes. The mass of the first isotope times the percentage of the first isotope. The second isotope times the percentage. The third isotope times its percentage, and then add all of them together and divide it over 100. I divide over 100 to just remove the percentage, okay, because I need it as a fraction. The percentage actually in physics and chemistry we call it the abundance of the isotope. نسبة الانتشار أو نسبة التواجد. So the abundance of the isotope is the percentage of this isotope in nature on the earth. On the earth, not on the universe. Because in the universe you might find different percentages. But here on the earth, okay, they take samples from different places on the earth or from different mines, من المناجم, okay, and they measure the average percentage or the average abundance for these elements. So let's take an example. Boron. Boron has 2 isotopes, boron 10 and boron 11. Boron 10 and boron 11. Boron 10 has mass. This should be the mass number, not the real mass. Okay? So has a mass around 10. And the boron 11 has a mass around 11. The abundance of boron 10 is 20%. The abundance of boron 11 is 80%. So if you have any sample of boron, and if you put it in a spectrometer, it's a device that can tell you what's the percentage of each isotope. Okay, so it will tell you on average that boron 10 is around 20% and boron 11 is around 80% of the sample. So let's calculate together the average mass of natural boron. So I will multiply the mass of the first one times its percentage, plus the mass of the second one times its percentage, divided by the total, the 100 to remove the percentage, and the answer is what? Can you do it, guys? If you have a calculator, please do it. And please, starting from today, you will need to bring a periodic table with you. We will need a periodic table every lecture. So there is a periodic table in the textbook at the last page. The last page of the textbook, it has a periodic table. And I think also chapter 16 has also another periodic table. Or you can print it from online or from the blackboard. There is a version on the blackboard. Okay, so what is the average mass? Did you do it?
10.8.
10.8 atomic mass unit. So the average mass of the natural boron on the Earth is 10.8 atomic mass unit. And this average mass is the one that's written in the periodic table. In the periodic table, they write down the atomic number and the average mass. Okay, why don't they write the mass number? Because we have multiple isotopes, so they will write the mass number of which one? So we have multiple isotopes. So instead of writing the mass numbers, they write the average mass of the element. Okay, so if we look to a periodic table here, look at the boron. It has 5 protons and the average mass is 10.811. We calculated 10.8 only. So why there is a difference between their calculations and our calculation? Do you know why?
Because there is different in percent.
There is difference in percent. That's a good idea. What else? They use the real mass of boron. They use the real mass of the boron isotopes. But we used what? We didn't use the real mass. We used what? Where is it? We used what? We used the mass numbers, not the real mass. And we said the real mass is a little bit different. So the difference here is because the percentage itself might be different. It might be, for example, 20.5 and maybe 79.5%. It depends on the average that they have. Okay. And because they use the real masses and we use the mass numbers. I will ask you to try to solve this one. Calculate the average atomic mass of chlorine if the abundance in nature is 75.77% for chlorine 35 and 24.23% for chlorine 37. So I will give you 30 seconds to do it yourself. Go ahead. When you finish, just let me what's the answer. Anybody?
35.4.
0.4 only. What's the next decimal number?
4846.
Okay, 48 or 4846. Okay, that's a good one. So here the average atomic mass, we multiply the first mass times first abundance, second mass times second abundance divided over 100, so it gives us 35.48, as you said, 46 atomic mass unit. If we look at the periodic table for chlorine, chlorine is here, so it's 35.453. There is a little bit difference. So where does the difference come from?
Additional.
The percentage and the real masses. They used real masses while we used what? We used mass numbers. The real masses are a little bit different. It might be like 35.01, okay, instead of 35. So using the mass numbers can work in the rough calculations, as I said. Let's take a different problem. What if I tell you that these percentages are not known? Okay, these percentages are not known, but what's known actually is the average mass. The average mass of chlorine is 35.4846, and there are two versions or two isotopes of chlorine, chlorine 35 and chlorine 37. Can you calculate the percentage or the abundance of each one? Yes. How to do that? I will say, assume the abundance of chlorine 35 to be X. So the abundance of chlorine 37 will be what? If the abundance of chlorine 35 is X, so what's the abundance of chlorine 37? 100 minus X. Okay, so this is the first assumption. One of them is X and one of them is 100 minus X. So this works if we have two isotopes. So let's do the equation. First mass times first abundance, which is X, plus second mass times second abundance, which is 100 minus X, divided over 100. It gives you 35.4846. Take the 100 to the other side. It will be 35,000 or 3,548.46. Okay. How to solve this equation? It becomes 35x plus 3700 minus 37x equals 3548.46. So negative 35 minus 37, it's negative 2 times x equals 3548.46 minus 3,700. This subtraction will give you a negative, so it will be cancelled with this negative, and I can find x. What's x? If you can get it, please. If you have a calculator. 75.77. So this is the percentage of the first one. Which one? X is the percentage of what? Of the chlorine 35. So this is the percentage of chlorine 35. That means the percentage of the other one is 100 minus 75.77. It gives you the 24.23%. So the other one is the 100 minus X, which is the percentage of chlorine 37. Do you understand this idea, guys? Huh? Okay. I want also you to understand something else. The 10.8 here, 10.8, is it closer to the 10 or closer to the 11? It's closer to the 11. It's very close to the 11. So why is that? What's the reason? Why 10.8 is very close to the 11?
Because the percentage of 11 is
high abundance. Because the abundance of the boron 11 is higher. What if they have the same abundance, like 50% and 50%? Instead of 20 and 80, what do you think will happen? The result will be 10.5. Okay, it will be in the middle exactly between the 10 and the 11. But because the abundance of the 11 is higher, it turns to be closer to the 11. You understand this point? So if you look in a periodic table, for example, like this one, And I ask you, look at nitrogen. What is the most common isotope of nitrogens? Is it nitrogen 13 or nitrogen 14 or nitrogen 15? The most abundant one or the most common one, 13 or 14 or 15? When you look at the average, it's 14.007. So it's very close to what? To the 14. That's right, to the 14. So the most common isotope of nitrogen is 14. What about carbon? What's the most common isotope of carbon? Huh? Very easy. 12. That's right. What's the most common isotope of oxygen? 16. The most common isotope of fluorine?
19.
19, and so on. So this idea might work for many elements, but not all of them. Not all of them take care of this issue. Okay? So in some elements you need to take care. Like here, the tellurium. Tellurium is its average mass is 127.6. So you might guess it's 128, maybe, but I'm not sure. Maybe there are multiple isotopes. Okay, like maybe it has like 3 or 4 or 5 isotopes. I don't know. Okay, so you cannot be sure that it will be 128. But for the oxygen or for the nitrogen or for the carbon, it's very obvious. It's very clear. Helium also, 4.003. That means helium 4 is the most common one, and so on. Okay, it's just a rough estimation. When you look at the periodic table, you might expect what's the most common isotope of this element. Okay, but don't use it for all the elements. The radioactive isotope. Sometimes the isotope is stable. And alhamdulillah, most of the isotopes around us are stable. Okay, but sometimes also it might be unstable. It might be unstable. And usually the instability of the isotopes, it happens when there is a big difference between the number of protons and the number of neutrons inside number of protons inside the nucleus. If the number is the same, the number of protons equals the number of neutrons, the element is stable. Like for example, carbon 12, it has 6 protons and 6 neutrons, very stable. Nitrogen 14, it has 7 protons and 7 neutrons, stable. Oxygen 16, it has 8 protons and 8 neutrons, very stable. Helium 4 has 2 protons and 2 neutrons, okay, very stable. Okay, but when there is a difference, a big difference between both, so the element tends to be unstable. When it reaches to a certain limit, the nucleus becomes unstable, and when it is unstable, it's called radioisotope or radioactive isotope. Nazir Musha'a. The radioactive isotope is unstable isotope which undergoes a radioactive decay. The radioactive decays, in general, they have multiple kinds like beta decay, or gamma decay, or alpha decay, or gamma emission. Sometimes it produces a neutron, sometimes the radioactive isotope produces a proton, sometimes it produces or it makes a fission, انشطار. Okay, so there are many ways to relax the unstable isotope. Relax it, تهدئته. Usually the most common, the element or the isotope produces beta particle or alpha particle associated with gamma decay or gamma emission. Gamma is a photon, while beta and alpha are particles. Beta, it's the same like an electron or something else called positron, which is the antimatter of electron, المادة المضادة. Okay, you don't need to know it for this course. Okay, but later, inshallah, when you study higher levels, you might know it. Alpha decay is a particle that has 4 nucleons. It has 2 protons and 2 neutrons. This is the one that Rutherford used in his gold foil experiment. You remember the gold foil experiment we have discussed in last lecture? He used a radioactive isotope which produces alpha particle. Okay, so it's unstable. It's called unstable isotope. Okay, it undergoes a radioactive decay. For example, carbon has 3 isotopes: carbon 12, 13, and 14. One of them is unstable. Which one of them is the unstable? What do you think? The carbon 12 or the 13 or the 14? If I tell you that one of them is unstable or one of them is radioisotope, what do you think? Which one of them? Can you guess? So the last one actually is the unstable one. Okay, the carbon 14 is the radioactive isotope. The first one has 6 protons and 6 neutrons. That's very stable. The second one has 6 protons and 7 neutrons. Actually, it's still stable. The third one has 6 protons and 8 neutrons, and it is unstable. So it undergoes a beta decay. And by the way, if you want to know it, beta decay in this case is a neutron changes to a proton, because the number of neutrons are 2 extra more than the protons. So a neutron inside the nucleus changes into a proton. So the number of proton increases to become 7, while the total number is still 14, because a neutron changes to a proton inside the nucleus. So it changes into another element which has 7 protons. What is it? Look at the periodic table, you will find that it's a nitrogen. So the carbon 14 changes into nitrogen. That's called decay. Decay, محلال. Okay? Because the element changes into another element. This radioactive isotope, we call it the parent, and the product is called the daughter. Another example is the hydrogen. Hydrogen has 3 isotopes. All of them, they have 1 proton. The first one has 1 neutron and 2 neutrons. Hydrogen 1, 2, and 3. So if I tell you that one of them also is unstable, so which one? The third one also. Hydrogen 1, 3, which is the tritium, is radioactive. So it decays by beta decay also. Okay? A neutron changes to a proton inside the nucleus. So the number of proton increases, it becomes 2, while the total number of nucleons are the same. So it stays 3. So it changes into another element that has 2 protons. What is this element? We call it the helium. If you look at the periodic table, 2 protons means it's a helium. So this is not the most common helium, by the way. The most common helium is helium-2,4. If you look at the periodic table, the average mass is, as we said 4 minutes ago or 5 minutes ago, 400, I think it was 2 or 3. That's the average mass. So the most common is the helium-4. But this is another helium. We call it helium-3. And it's a stable. It is a stable helium. So the parent is the tritium and the daughter is the helium. This issue, this radioactive decay, takes time. So to define the activity or the radioactivity of a radioisotope, they define what we call half-life. The half-life. What is the half-life? It's the time required, or the period of time required, for half of the elements or half of the atoms of the parent to change into daughter. So if we have 1 kilogram of the parent, after this time, which we call it the half-life, it will be half kilogram. And where is the other half? Changes into a daughter. Like carbon 14 changes into nitrogen. So half kilogram will be nitrogen and the other half stays carbon as it is. Also the hydrogen 3, the tritium. Half of kilogram will become helium 3 and half of kilogram will stay as it is. The half-lives are measured for all the isotopes that we know. So for example, hydrogen, it's around 12.3 years. This is the half-life for the tritium. For the carbon-14, it's 5,730 years. So every 5,730 years, half of the amount of carbon-14 changes into nitrogen-14 and the other half stays as it is. So that's called the half-life. So if we start with 1 kilogram of carbon-14, after 5,730 years, it becomes half kilogram. Then after another 5,730 years, the half becomes quarter. It loses its half. The half loses its half. So like each time you multiply times a half. Then after another 5,730 years, it loses its half. So half of the quarter is 1/8. So the 1 kilogram becomes 1/2, then becomes 1/4, then becomes 1/16, 1/8, then becomes 1/16, and so on. So we can consider it as 1/2 to the power of n. Okay? So this is the decay of the parent. And there is an equation that we might use to calculate the remaining of any mass. The remaining of the mass equals 1/2 to the power of n times the original mass. This equation is very important. So for example, if we start with 60 grams of a certain isotope, this neptunium-240, you don't need to know the name. How much neptunium-240 will remain after 4 hours if the half-life is 1 hour? So how many half-lives do we have here? 4 half-lives. So n equals 4 half-lives. So the 60 gram, after 1 hour, it becomes 30 gram. Then after 1 hour, becomes 15 gram. Then after 1 hour, becomes 7.5 gram. Then after the 4th hour, it becomes 3.75 grams. And so on. How to calculate it mathematically? From this equation. 1/2 to the power of 4 times the original mass, it gives you 60/16, it gives you 3.75 grams. So this is the leftover of the neptunium-240. So out of the 60 gram, only 3 gram or 3.75 gram is left. Okay, guys? So that's everything today. If you still have questions, please go ahead and ask me. Thank you so much.